So this is the chemical reactions that go on. NMHC stands for non-methane hydrocarbons, VOC. Reacts with the hydroxyl radical in the atmosphere to produce a peroxy organic radical. Peroxy organic radical. This peroxy organic radical reacts with the second species, which is the nitric oxide, NOx, that I talked about, to give us NO2, nitrogen dioxide. This is what is emitted by automotive exhaust. This is what gets formed in the atmosphere. And the photolysis, that is HNu, this means sunlight, that is NO2 reacting with sunlight, produces ozone. So in essence, the two precursors, NOx and VOCs, reacting in presence of sunlight, produce ozone. Now, let me take it one step further in terms of the chemistry, and I will stop with the chemistry after this. The chemistry of the global atmosphere is controlled by this guy, which is OH, the hydroxyl radical that I showed you a moment ago. That's what controls almost all the chemistry that goes on in the global atmosphere. Hydroxyl radical reacts with SO2, which is emitted by power plants, to produce sulfuric acid, which leads to sulfates. Hydroxyl radical reacts with the VOCs to produce secondary organic aerosols, but it also produces peroxy hydroxyl radical that I showed you a moment ago. Peroxy hydroxyl radical reacts with NO to produce NO2, which is photolyzed to give us the ozone. And along the way, we produce nitric acid and hydrogen peroxide, H2O2. Now, this is where the role of ammonia comes in. Ammonia, which is emitted by agricultural processes predominantly. 98% of all ammonia, at least in North Carolina, comes from agricultural processes. And that reacts with nitric acid, that reacts with sulfuric acid, that reacts with organic acids to produce the corresponding aerosols, which are very harmful to human health. This is what the change in ozone during the day looks like. Going from 12 midnight to 12 midnight, this is 12 noon here. So sunlight is required to produce ozone, as I explained to you a moment ago. Therefore, concentrations of troposphere ozone are normally high during the afternoons and during the summer months when sunlight is more intense. And that's exactly what we see. At night, ozone concentration is low. When the sunlight comes out, it begins to rise, and shortly after noon, it peaks and drops back down again. So the diurnal profile of ozone, no matter where you go, except at high elevation, and I'll show you that in a minute, will look something like this. And as you increase the temperature, i.e. during summer, it'll even be larger amounts of ozone being produced because we have more sunlight in the northern hemisphere during summer. This is what happens when you are on a mountain. Okay, and these measurements were made in Asheville, which is, so if you can think of the mountain as a tall tower, and in fact, Mount Mitchell is 2,000 meters tall. So if you can think of it that way, the base of the mountain is low elevation, so we see a diurnal profile. As you start going up the mountain at 1760 meters high, there is no profile whatsoever. It's relatively constant. So that means you are being exposed at high elevation to ozone values, high values all the time. And as you go even higher in elevation, the profile reverses itself. That is, at night, there is more ozone than during the day. Now, that might seemingly seem like a paradox, but it isn't, actually. And there is a good explanation for that. And 10 years ago, when my research group was working on Mount Mitchell as part of mountain cloud chemistry program, we observed that and we were able to explain this rather meaningfully. And what we see in this slide is the distribution of ozone on planet Earth. Southern Hemisphere, South Pole, Samoa, these are all Southern Hemisphere locations, and Northern Hemisphere locations. We see more ozone in the Northern Hemisphere than in the Southern Hemisphere. And that stands to reason, because in the Northern Hemisphere, we have more industrial activity, more automobiles, more utilities, and Southern Hemisphere, we don't. So the distribution of ozone in the Southern Hemisphere is considerably lesser than it is in the Northern Hemisphere. Now, to control a pollutant, the US Environmental Protection Agency has put forward what is called the National Ambient Air Quality Standard. And ozone is a criteria pollutant, which means there is a national ambient air quality standard for ozone, both a primary standard and a secondary standard. Primary standard means it is set to limits to protect public health, whereas secondary standard is set to protect public welfare. So our welfare, which is vegetation and material and the like, is protected by the secondary standard, and the primary standard is set for human health related issues. And here is the standard for ozone. Up until 1997, the ozone standard was 0.12 ppm, not to exceed 0.12 ppm concentration over 1 hour. So you measured concentration of ozone continuously, averaged it over 1 hour, and if that value was less than 0.12 ppm, you were in good shape. However, it exceeded 0.12 ppm, then you had an exceedance. And if you had 3 exceedances over 3 years, then you had a violation. So that's how we keep a track of it. However, the standard was changed in 1997. Instead of a 1 hour standard, it was made into an 8 hour standard, and the value was 0.08. Because the argument that was made was, well, we are exposed not to high values all the time, we are exposed to a band of value all the time, and what is this average value that we are exposed to? Is that more detrimental to us? And then in 2008, the standard was tightened even further, and so the new ozone standard that we are operating under now is 0.075 ppm, not to be exceeded for 8-hour averages of ozone concentration. That's the new standard. And so here are some of the effects and consequences of these effects. Once again, ozone is formed by the interaction of NOx, oxides of nitrogen, is presence of volatile organic compounds, and the sunlight is what triggers this reaction to give us ozone. Okay. It has an impact on vegetation, and you can see how the crops begin to be affected. The Beijing Olympics, 2008, the main issue in terms of Beijing Olympic that caught the imagination of the world was the smog in Beijing, and it was largely ozone.